Well, good afternoon, everyone. My name is Cristian Ledesma. I am an associate professor at the Pontificia Universidad Católica de Chile, and today I have the opportunity to show to you some of the results of a recent research that was conducted by my former student, Mr. Álvaro Gutiérrez, and also the results that were developed with the help of Ángel Martinez from Miras. Now, this presentation has basically three parts that I'm going to explain to you later. But first of all, I would like to thank, the Ángel and Álvaro for all their help in order to put this presentation together. Now, the content is divided into three main topics, with the first an introduction to the problem and also to the case history that I'm going to show you. Then are going to be aspects related to the numerical modeling of the problem, and then some discussion about the results that were obtained with this analysis that were performed not only with Miras but also with FLAG2D. Now, the case history that I'm going to show you a little bit later is one that was observed during the 2010 8.8 magnitude earthquake that we had here in Chile. As you probably know, and if you don't, well, maybe this is a good occasion to tell you a little bit about it. This was a rather large earthquake here in Chile. It affected an area that was around 5 to 6 kilometers long and probably 1 to 200 kilometers wide. Okay, and here you see what is the main shock mechanism and also the number of aftershocks that occurred after the first 48 hours and then the ones after the following hours after the 2 days. And as you can see, the area that was affected was rather extensive. A lot of damage was caused by the earthquake, not only in dealing with the things that we're going to be looking today, with liquefaction and breaches and that kind of structures, but also in terms of buildings and also port structures and some others that you probably have seen in some previous reports. Now, in this case, and for this presentation, I'm going to focus on liquefaction of soils, okay, and the effects that liquefaction has on pile-supported structures. Now, when I talk about liquefaction, I like to use this definition by Marcuson in 1978 about the transformation of a solid material that used to be, let's say that has had some stiffness and some strength to offer to whatever kind of structure you had to put on top of it. And then because of the occurrence of liquefaction, there is a change of state from a solid material to a liquefied one as a consequence, of course, of the increment of pore pressures and the consequence of reduction of effective stress during earthquakes or during some sort of event. In this case, it's earthquakes. Now, in this plot that you see, in this figure that you see at the right, the idea is that when you have a material that is basically sandy material, maybe some silts or some fine gravels that are in loose condition, so you have enough space here to reaccommodate the particles once you have a certain amount of shaking. But when this material is also saturated, when the shaking comes in and these big arrows try to show that type of deformation that this soil mass can have, the particles tend to reaccommodate, and as they try to move and fill in these spaces, they find water. And the water, within the number of seconds where you have the earthquake happening, cannot just flow and move away of the path of this particle. So what happens is, as the particles try to reaccommodate, the pressure in the water goes up. And if it goes up enough, you can have a reduction in effective stress that can actually take the number close to 0 or to 0 eventually, so you can have a separation, so you lose contact between the particles and the particles start to float in a liquid phase. Okay, so of course the reduction in strength and stiffness is a clear consequence of liquefaction occurrence. Now, this is of course nothing new. I mean, this was studied, in a lot of detail in the 60s. I mean, with a lot of work by a number of people like Professor Ishihara or Harry Bolton-Sid, just to name two of them. And the idea here to show you these two plots is just to try to see in a simplified format how liquefaction is seen by the soil when you look at it closely. So you can imagine that whatever is up here, which is in this horizontal axis, you have time, and here you have the deviatoric stress normalized by a certain effective stress. So if you take a soil sample like this one and you put it under a torsional shear test kind of condition, and you applied a constant shear stress on the sample, I mean, as you keep on loading the sample, at some point, I mean, after a certain number of cycles, you may start observing, or the soil shows an increment of the shear strain. So if you see, the load is really not going up, but as you load it and load it, what happens in the soil is that the particles tend to reaccommodate. As they do that, the pore pressure goes up, and this is the thing that is shown here at the very bottom. You have the excess pore pressure also normalized. As you know, if this number goes up to 1, that's when you reach liquefaction. And here, as the number of cycles goes up, you see that this excess pore pressure builds up continuously. And when this number goes very close to 1, that's when you start having this reduction in stiffness, and of course a reduction also in strength of the material. Now, in the case of Chile, the Maule earthquake, the 8.8 earthquake, because of that earthquake, a number of sites experienced liquefaction, and this is a summary plot prepared by Professor Ramon Verdugo here in Chile, where you see that in this rectangle you have the fault rupture area. Now, if you see, in a number of places, I mean, liquefaction was observed in different ways. You could see that it occurred in relatively flat ground, also in the form of lateral spreading, which is going to be the topic of my talk. Now, you could see in some bridges and some ports and dams, some buried structures that because of this just popped up to the surface, some slope failures, some access in roads, and some reclaimed land. So a number of sites experienced liquefaction, and one of these, it was close to this area of Constitución. Okay, so it's really in the area of Maitakito. Maitakito is an area that is very close to the epicenter, if you want to look at that way, for this earthquake. So it was affected by a number of cycles, large accelerations. So it was a pretty intense loading in terms of shaking. Not only that, I mean, along the coast, that's the area that was really affected by the tsunami also. Now, in this kind of situation, and looking at this lateral spreading thing, and also looking at the type of structure that I'm going to explain to you a little bit later, I wanted to bring in this figure I prepared some time ago, just trying to explain like the main problem that you may have when you have a certain structure, like in this case a bridge deck, that is supported on piles, and these piles are long enough to go across a liquefiable layer and then go beneath that layer and get embedded into this dense material. Now, and you do that, of course, because you want to transfer the load of the upper structure down to the competent soil. Okay. Now, when you do this in this type of structure, the abutments, where you have a fill and this slope, and when the earthquake hits this structure, you may experience liquefaction on this layer. This is a particular layer that is susceptible to liquefaction, And if liquefaction takes place, all the soil mass that is above the liquefiable layer will tend to slide towards the right, in this case towards, let's say, the river. Okay. Now, as the system does that, because, and why it works that way, because now you have a weak layer here, and this slope will, this is like a potential failure surface that may take place. If the soil mass wants to do this, wants to displace laterally, it's gonna take the structure and it's gonna move it with it. Okay, and this is what is shown here. This vertical position would be the initial one. This would be the deformed one. Now, as the soil mass takes the structure and wants to move it towards the right in this figure, what happens is the piles start to bend. Okay, so they are deflected laterally, like it's shown here, and when that happens, the piles actually try to react against the lateral movement that is going to the right. When you deform the piles this way, the piles try to go back to the left, so they try to restrain the movement. This is what is called the pile pinning effect, because the piles pin the upper structure in the dense layer here at the very bottom. Okay, so you need long piles embedded in good soils to have this kind of effect. That is, the piles not only work in the vertical way, the more usual one, or supporting lateral loads coming from the upper structure, but in this case, they're also helping in trying to stabilize this slope that is formed here at the bottom. The figure that you see here at the right bottom is a simplified method that was proposed a number of years ago and that has been analyzed after that, where if you look at this problem in a very simplified way, you can think of it as as two separate problems that are somehow connected. One of the not the problem, but one of the systems that is working here is the pile system, is the pile group, that as you displace it, it's gonna have some shear loads developing in the piles that are going to react against the slope. That is the figure, the curve that you see here, that is called pile response. This is as you increase the abutment displacement, you get more shear force in the piles. Okay, because of this double fixity kind of figure here, we have displacement of the upper part of the piles. Now, on the other hand, from the point of view of the slope or the abutment structure, as you have a restraining force that is larger and larger, the expected amount of displacement that this system is going to have is going to get reduced. So you can think of like an external load that is going to restrain the movement of this system, that as this force goes up, the displacement that you're going to have is going to get reduced. This kind of decoupled behavior, one coming from the slope / abutment and the other one coming from the piles. I mean, the idea is that if you draw those two curves correctly, at the point that these two curves cross, that's where you get the compatible displacement of the piles and also of the slope / abutment, and that would be the expected residual level of lateral displacement for a problem like the one that is shown here in the figure. Now, why am I paying too much attention to this? Because this is part of what happened in the case history that I'm going to talk about. This is a cartoon showing the condition of the Maitakito bridge that was affected by the 2010 magnitude 8.8 earthquake here in Chile. It is, you can see, you have 1, 2, 3, 4, 5, 6, 7, 8. It's 8 spans. Okay, the total length of the bridge was not that long. I mean, it was around 300 meters or so. And as you see here, the thick black line that is at the top, that represents the bridge deck. Then you have a system of the piers and also piles under the bridge piers, and then you see the structure that was used for the abutment, This is for the north end, that is was called close to the city of Iloca, and the other one close to the city of Kivoldo. Now, if you take a look at the simplified soil profiles that were found in the site, the upper part of this material, well, of course you have the fields that are the abutments, but in terms of natural soils, what you have is you have an upper loose sand, okay, that is marked with yellow here. Underneath that layer, you have a medium sand, and then you have a gravel deposit that is rather dense, okay. The yellow material that is here at the top, that was the one that is liquefiable. Then you have a medium sand, and then you have gravel that is, I mean, more or less in between of gravel. It didn't have any values of SPT or whatever to show that it's susceptible to liquefaction, but the yellow one did have that kind of behavior. Now, you see here the borings that were made. Initially, 3 borings were made, S1, S2, and S3, and after in the second phase of the project, deeper borings were performed. They were called S1A, S3A, and S2A. Now, if you take a look here at the bottom left, you see the SPT profiles versus depth. For each one of those borings, you have S1 and S2A all together. I mean, they pretty much look similar here in the upper part. And then if you take a look at the scale, you have 25 blows per foot, and then you have 50 and 75. So 25 would be a rather dense or medium dense sand in this condition, and you see numbers that are around that number, and then numbers that go above that. Then same thing for S2 and S3A, and similar thing for S3 and S1A, the SPT profiles. So for this structure, we performed a liquefaction susceptibility analysis to try to identify what would be the layers that are likely to liquefy. And of course, that's what we found. We found that the yellow one that is marked here is the material that is susceptible to liquefaction. For this analysis, we used a PGA of 0.4 G, which is the closest station measured for this area. I mean, in 0.4 G was rather usual number for the earthquake we had 7 years ago. And if you use the 0.4 G and you use, let's say, the latest, the Bollinger and Adris liquefaction susceptibility plot using SPT, that is going to give you a high CSR value that really, I mean, it's going to anticipate the occurrence of liquefaction for everything that has an SPT of, let's say, 28 or 27 blows per foot. I mean, any sandy material that is below that number, according to that procedure, was going to experiment liquefaction. This is what you see in terms of factor of safety against liquefaction. Here in the 3 figures on the right, here is the factor of safety of 1, marked with the red line vertical, and of course everything that is to the left of that line is anticipated to liquefy in this condition. Okay, here you have liquefaction down to a depth of, let's say, I don't know, 9 meters or something like that, depending on the boring. Okay, but in this case, what happens is that liquefaction is concentrated in the upper material, and the material that is below a certain depth is not susceptible to liquefaction. This is very important because we're also looking with some other student situations that are a bit more complicated than this, where you have layers of liquefiable, then non-liquefiable, then again liquefiable, and so on, and that makes procedures like the one that I showed you, I'm sorry, the ones that I showed you here, a bit more complicated. For this simplified approach, you need the piles to go down and get embedded into non-liquefiable material. If you keep on going, having liquefiable layers, procedures like this are little bit harder to implement, I would say. Now, okay. Now, if you apply this type of approach with these two curves crossing here and first try to come up with some simplified estimate of what would be the residual lateral displacement for the bridge, this is the kind of result that you get. Okay, this is just trying to get a first sense of what this would look like. Now, why do you see so many curves going from here 0, 0 to the right, and then so many coming from up here down here? It's because we use different procedures, not only for the lateral pile behavior, but also for the slope stability. So because you all know that every procedure has different assumptions, and we wanted to see how those assumptions affected the end result. And what you see here is a range of results. Okay, if you take a look at, let's say, these curves going down, and here is some kind of uncertainty around that, and you see those curves going like this. Here, I mean, it depends really on the procedures you want to take a look at, but this procedure will probably tell you that the residual lateral displacement is going to be in the order of 10 centimeters. Okay, so about 4 inches. However, the displacement that was observed in this bridge, in this Maitakito bridge, was of less than 2 inches, probably even, I mean, less than that. So, although the procedures, or this type of procedures, are simple enough and fast enough to implement, they do tend to, and at least in this case, to give you a rather conservative result and also a lot of uncertainty. Okay. Now, you can use this not only for bridges, and this is just another example. This is another case history. I'm not going to talk too much about it, but in this case, it is a port structure that was affected by the same phenomenon. You have the deck of the port, you have the steel piles going down, and you had an issue of lateral displacement that caused this type of deformation on the system. And if you see, if we use the same idea, I mean, here you have the structure, you have certain material that had the tendency to liquefy and to slide laterally on top of material that didn't have such high susceptibility to liquefy. But when this happens, this soil pushes the structure and it deforms it, and you can use more or less the same type of approach that I showed you with the two curves to try to get some estimates of residual lateral displacement and, of course, bending moments on the piles and some shear forces. And this is what is shown here again for the port, where you have different methods and simplified ones compared against some finite element methods that were implemented using Plaxis 2D in this case. Okay, this is from another Master of Science student of our university, just trying to give you a sense of the difference that you may get between simplified methods and the use of numerical methods, like in this case. Okay, now let's go back to our Maitakito bridge. This is the same figure that I already showed you, and now it's just going to show you what were the effects of the of liquefaction in this case. Maybe tell you a little bit more that, well, here you have the Maitakito. Well, maybe you don't see it too clearly, but these blue lines represent the Maitakito River that flows into the Pacific Ocean. And in the case of the abutments, because we're going to focus our attention on the abutments, each one of them is supported by 2 rows of 4 drill shafts having a circular cross section. Okay, here you see the 2 rows, and every row has 4 piles, and these were reinforced concrete drill shafts, and they were rather long, I would say. I mean, compared to some other designs that we have seen in our country. And the main reason was really, well, from what I was told, that was not really because of liquefaction, but they were worried about scour due to the river flow. I mean, this is a river that from time to time has a lot of flow, and the erosion of the material was really the concern here. So they made the piles rather long to avoid having issues in that regard. But in this case, they also serve well for the purpose of lateral spreading and the control of the deformation. As you can see here in figures B1, B2, B3, really the amount of residual lateral displacement was rather minimal. Here you see the handrails of the bridge that are they overlapped. I mean, they knock each other, creating these small failures here, okay, with displacement that from our estimates were not larger than 2 inches or so. Here you see the abutment structure showing no distress or no major deformations, despite the evidence in this area of the occurrence of liquefaction and lateral spreading. I mean, there were sand boils, there was cracking on the ground, and there was displacement and pushing of the ground that was above the groundwater table pushing against the structure. However, the structure was stiff enough and the piles were long enough to control and to limit that amount of deformation. So the idea with this study was to try to see if we could do better, okay? Try to see if we can understand a little bit better what happened in this case and why this system worked more or less okay. Now, so the scope of the study, I mean, we had different steps and different things to do here. Is first we had to do some geotechnical characterization, mainly using the information coming from the borings. Then we used and we developed numerical models, I mean dynamic ones, using finite elements. This was the model using Midas, and then using finite differences, using flat 2D, and also because of let's say the easy way to from a 2D model to develop a 3D one, we also use Midas to create a 3D model of the same problem and try to make a comparison against, I mean, between 2D and 3D, and try to get a handle of how that was reflected in the analysis. Okay, in terms of the liquefiable soils, we used UBC sand, which is a constitutive model that was developed specifically to try to mimic and to the behavior of the liquefiable soils. Now, what you see here to the right is the Midas model, the 2D one, okay, showing the main components. I'm going to go back to this in a moment, but you see here the abutment, the structure, and the piles and the different layers of soil. And this is just some screenshots of some of the results that I'm going to go back and I'm going to explain to you a little bit later. Now, I already explained this. To perform the susceptibility analysis for liquefaction, we used the SPT data that we had available. Here, I would like to just make a quick comment. I mean, this is going to be also in the conclusions, but although developing a numerical model, of course, it's going to take a bit more time than trying to use these simplified methods. The idea of using numerical models to capture properly the static condition of a structure like this, and also trying to anticipate what would be the dynamic behavior, taking into consideration all the components at the same time, not using decoupled type of analysis. It's really, I mean, it has a lot of advantages because it gives really, gives sense to the physics of the problem, as I will explain a bit later. Okay. Now, for the most part, for the UBC sand parameters, this is also there is a table coming a little bit later. We use the SPT data, and if we didn't have SPT data, we had to use some information from the literature, some correlations and things like that. Also, especially for the non-liquefiable layers. I mean, the non-liquefiable ones, we just modeled them using a more Coulomb, I mean, elastoplastic kind of modeling, which Well, in this case, since we didn't expect to see too much failure, deformation, or something like that in these soils, it proved to be, a reasonable assumption. Okay, if you have a combination, maybe you wanna try to use something a little bit different. Now, in terms of the analysis that were used, let's say the first one, this was only done only using FLAC 2D. We wanted to see what happened if we took the initial geometry of the problem and we switched the properties of the liquefiable material from the initial ones to the liquefiable ones, and try to see how the system and how the model came down to equilibrium again. Okay, and what type of deformation and what type of things, we would see. Okay, so the idea, we just turned on, or no, not turned on, we modified the properties of the liquefiable soil, well, of course, right after finishing the gravity and the static condition. Of course, you have to build this in steps. First of all, you have the natural soils, then you put the fill, and then you put the structure on top, and then only with the gravity acting, you let the model reach equilibrium. Right after you do that, and here I'm thinking a little bit about FLAC, you change the properties of the liquefiable soil and then let it go and see what type of equilibrium condition the system finds. To do that, for the liquefiable material, we used Poisson's ratio of around 0.5, or of course a little bit less than that, and we assigned a residual undrained shear strength for the liquefiable soil based on an average of different methods. Okay, if you want to have more information about this, I will be happy to share that and to give it to Midas for sharing. Now, in terms of dynamic, because this was purely kinematical, I would say. There was no inertia, no shaking involved. In the case of the dynamic, we used FLAC and Midas. For FLAC, we use only the 2D model and UBC sand. And for Midas, we use 2D and 3D. For FLAC, I'm not going to show all the results, but we used UBC sand, but also we checked that response with PM4 sand and also UBC Hist plus a fish function that was developed. But let's say we have FLAC kinematic, FLAC dynamic with UBC sand and a 2D model. We have Midas 2D with UBC sand and Midas 3D also with UBC sand. Okay, and this is just a numbering of the piers that were analyzed. Okay, so going from from Iloca, so this is from north to south. You have piers 1, 2, then piles 1, 2, and then piers 1 to 7, and then piles 3 and 4. Now, I already mentioned that to do this, we just used information coming from the SPT. We knew what the liquefiable layers were, and then also we used some information coming from a lab test and shear wave velocities at this site. Now, this is a view of how the models look like. This is using FLAC in this case. You can see the soil layers. You see what is the size of the model. 100 meters tall, and with the vertical borders away from the bridge. Away enough so that the borders didn't affect what was going on with the bridge, and also that didn't affect the behavior of the liquefiable material here. In terms of boundaries, 3 field boundaries were used at the vertical borders, and an absorbent boundary was used here at the bottom. This is talking about FLAC, and also we used beam and piles elements for these vertical ones, and then we modeled the structure of the abutment, the wall, and the foundation using finite the zones that FLAC has. Okay, so this is the overall view of that model. Now, if you take a look at Midas, the ideas are more or less the same. You have the abutment structure, you have embedded beam elements to model the piles, then you have the fill, the liquefiable layer, and then you have the non-liquefiable one and the gravel. At the bottom you have dampers to avoid the reflection of the waves, and also you have in here at the bottom, it's where you put the input ground motion that was selected based on rock ground motions nearby, and that was also was modified, really was de-amplified, so that in terms of what happens in the free field more or less reached a 0.4 G. In the vertical ends of the model, we used free field condition coming from Midas. Now, for the maximum size of the elements, we use this recommendation that for one wavelength, you want to have at least, I don't know, around 8 elements. Okay, if you do that, I mean, or if you want to do that, of course, you need to combine to get the wavelength. You need to combine what is the lowest shear wave velocity in the model with the highest frequency that you're interested in taking a look at. Okay. Now, if you combine that information from this model, you need elements to reach that condition of having around 8, maybe a bit more elements per wavelength. You need elements in the order of less than 1 meter or so. Okay, so because I mean the lowest shear wave velocity was related to the liquefiable layer, and the highest frequency had to do with the frequencies coming from the earthquake. Now, when you look at calibration, this is how the UBC SEND model looks like. I mean, at least in general. I mean, it's a model that if you, many parameters are connected to the SPT blow counts. So in this case, if you see how this is just a numerical model of a test of this sandy material, which is saturated and loose with blow counts of 5, 10, and 15. If you take a look at how the excess pore pressures develop with a number of cycles, when you have a low blow counts, you have that this with a small number of cycles you reach one rather easily, and if you increase the number of blow counts, this takes more cycles to get to that same condition. Now, if you express that in terms of shear stress versus shear strain, okay, you get loops that are of course different. Okay, the blue ones, I mean, is the one that is the weakest, or the soil that is most susceptible to liquefaction for this analysis, and you have that you reach these banana loops rather easily. If you take a look at the red lines, you get a few cycles that really show no liquefaction occurrence, and then after a certain number of cycles, you again get the banana loops cycles. Okay, so this is type of behavior that you get typically if you use UBC SEND. Now, how does this look like when you compare what UBC SEND looks in Midas and how it looks like in FLAC? Okay, here is exactly the same test with the same SPT, the same parameters, and here's a comparison between FLAC and Midas. And here's something, well, I think it's important to realize that even though we're using the same constitutive model with the same input parameters for the constitutive model and a simple test for the soil, I mean here just a cyclic shear test, what happens is you observe that the curves are not really on top of each other. There is some difference. This is only because of the different ways that the model is implemented in both programs. And you look at this in terms of these plots here, where you have the shear stress in the vertical and the effective stress at the bottom, or if you take a look at the loops. Okay, so this is just to tell you that if you are involved in one large project, I mean, you don't only want to do and try different constitutive models for liquefaction. Let's say UBC SEND and PM4 SEND. You also might want to take a look at different software, if it's available, to try to compare. It's not that this is going to create like large differences. I mean, you really cannot be sure what's going to be the effect, but it's good to have that comparison at hand if possible. Now, looking at the parameters, this is just a list of the parameters that are needed for the implementation of UBC send. This is a description of the parameters, and these are just some references. Now, if you see some of the equations and some of the recommendations that are that come with the UBC send model, you see that many parameters, I mean, are related to N160. Okay, so to the corrected SPT blow count, corrected by confinement and also by energy. Also in terms of phi, well, of course, you can relate that to N160. Then if you have some sort of stiffness here, also related to SPT, same thing here, same thing here. So really, I mean, many of the parameters, you can estimate them if you use this type of model coming from the results of a test that is rather, common for most projects that are deal with liquefaction. Because if you suspect or you think that you have a deposit that is going to suffer liquefaction, it's very likely that you're going to use SPT, CPT, or or shear wave velocity measurements. So if you use SPT data, you already have the information required to develop the variables and the parameters that go into UBC send. Now, there are some other parameters here. This is the post-liquefaction calibration factor and the soil densification factor that are not they're not really good recommendations or correlations with SPT, but more or less they really give you a certain number that you can use. But the idea with these two in our case is that you can use those to calibrate the results of whatever test results you may have from the lab, and you want to achieve a good match with whatever you have in the numerical model. You can go ahead and modify this a little. Of course, you can modify more than that, but these two showed to be useful in that sense. Now, if we go to results, if you think about this is the purely kinematical model, the one that I mentioned a few slides earlier, dealing with flag 2D and also changing the properties from non-liquefiable to liquefiable one, and also and just letting the gravity work. If you do that, what happens is you get this is lateral displacement, okay, in centimeters, in the north and in the south abutment. If here you see the numbers are in the order of 3 centimeters, 8 centimeters, and 3, which is really not that far off from what was observed, but it was a little bit smaller than that, okay? And here the idea is that when you take a look at a purely kinematical approach like this one, which is it's already a numerical model, but if you don't consider the shaking and the inertial forces, you're losing something, okay? Now, if you take a look at what happens in terms of bending moments on the piles, I mean, again, here you have certain numbers that are going to have more sense once we compare them with the resistance of the piles against bending, okay? Now, the purely kinematical model, this flag 2D model, it captures the effects of liquefaction. Of course, you have lateral spreading, you have pushing of soil against the structure, and you do have some deformations and bending. But it loses some key information. And of course, there is no time here, dynamic time, and there's no information about how, I don't know, the pore pressures develop in the model or something like that. Now, if you go at the comparison between the Midas 2D and the flag 2D model, and this is dynamic, okay, this is not purely kinematical, this is real shaking. And if you look at what are the bending moments that are the maximum ones that are developed in Midas and in flag, you see first of all that the distribution of bending moment along the piles is very similar, and also the difference between one model and the other is not that large. It's in the order of 5% in terms of bending moments. If also you take a look at what are the liquefied areas in the area of the abutment, you see that are very similar. This is Midas, this is flag 2D. Of course, like in any numerical model that does dynamic, you can, monitor what happens, sorry, in different points in the model. Here is just an example of the type of plots that you can get in from Midas. I mean, looking at points really close to the edge of the abutment, here at the liquefiable, sorry, at the top of the liquefiable, in the liquefiable material, and so on. This is just time, and this is some accelerations. If you see the evolution of liquefaction in Midas, I mean, you can get plots that look like this. Here is the initial condition in terms of excess pore pressure, and then you have what happens at 5 seconds, 10 seconds, 15 seconds, and 20 seconds of the earthquake. You see that at 20 seconds, most of the liquefiable layer is already liquefied. Okay, if we go back, let's see, go back here to the model, you see this is the liquefiable layer. So after 20 seconds of the earthquake, at least using this model, that's when you reach full liquefaction of the this layer. Okay, if that moment is the same as when you start having large inertial forces in the upper structure, you may have some issues here. Okay, and that's the idea of doing a fully coupled type of analysis. Now, if you see at a maximum shear strains, okay, you can get plots like this. There are some concentrations here at the top and also at the bottom of the liquefiable material. Okay, this is the type of results you can get out of a model like this one. Now, if you sorry, if we take a look at residual lateral displacement using flag and Midas, using these models, you see that the difference, I mean, it's not that large. I mean, you see residual displacement that are in the order of the 5 centimeters that I was telling you about that were observed in the breach due to the earthquake. And then you have the displacement that goes down, of course, as you go deeper into the ground. Using Midas, you can get animations of lateral displacement and also with bending moments. I'm trying to show you a little bit of that. Okay, here you have the video showing how the lateral displacements evolve in the piles. Okay, see, here's the shaking starting, and then you have more shaking coming in, and then liquefaction kicks in, and you see that the displacements start to accumulate towards the river in this case. Now, okay, and the colors represent the intensity of that of those displacements. Okay, and if we go back to the presentation here and we go to the second video, you're gonna see something similar in terms of bending moments. I'm sorry about that. Not sure what happened here. Okay, I'm sorry, but I'm going to send this video to Angel so that he can share it with you. But the idea is that the same type of plot that you can get for displacement, you can get it for bending moments on the piles. Okay, which really is the evolution of this plot here. Okay, this is just the situation where you had the maximum bending moment. Now, more results. Here's coming from flag. This is the evolution of pore pressures at 25 seconds, 88. I'm sorry, using flag 2D, using PM4 sand, using UBC sand. This is just as a reference. We're just focusing our attention to UBC sand in this exercise. If you look at the results of coming from Midas and also coming from flag, you see the pattern of lateral displacement and also from the pattern of post-seismic bending moment. Okay, you see different patterns here. This is really coming from FLAC, but is for the dynamic one is really similar to the one that we did with Midas. And one of the important things that you see here and that you don't see in the simplified approach or in the purely kinematical model is that you see the history of the bending moments getting developed on the piles. And this thick black line here represents the what we expect to be the bending strength of the piles and bending resistance. And if you see here, depending on the model that you look at, you see that the moments get larger and larger, and during shaking, there are some points that, and based on this model, go above that resistance. The residual ones are really far from the resistance, but during the earthquake, you may reach some large bending moments. And this is telling you that inertial forces are important. It's not only that you have liquefaction and the tendency of to have lateral spreading, but also the shaking is irrelevant in this type of situation. So, I mean, the concept of trying to do a decoupled analysis and really simplified, even for this case, which is simple one, it is a short bridge where you have only one layer of liquefiable material. Even in that situation, I mean, you may have issues like the one that I'm showing right here. Now, moving into the 3D, this is something that we did only using Midas. We just used the 2D model and we extruded in the perpendicular plane of the 2D model, and we did that to see what would be the difference in terms of behavior. And of course, there are some differences because once you turn on the 3D effect, you don't only have displacements along the longitudinal direction of the bridge, but also you get displacement in the transverse direction. Okay, so the displacements are not confined to only occur on the 2D plane, but they can also take place in the other one, which really reduces typically reduces the demand on the bridge. Okay, because if you have a certain amount of displacement in the longitudinal direction, and if you the soil sees the opportunity to not only push the bridge but also go sideways, I mean, portion of the soil is going to do that, and that's something that is going to be shown in part of in figure that is coming up. Now here is the timeline: 0, 20 seconds, 30 seconds, and here you can see the evolution of pore pressure generation. Okay, you see that the pore pressure starts here at the shallow layers that are in front of the abutment, and then as time goes by and the shaking takes place, this liquefied area gets larger and the pore pressures start to migrate under the abutment, and you have a pore pressure increment that is enough to create liquefaction here. But timing is not that it happens all at the same time, but it evolves with time. Now, with this type of model, you can also get results in terms of bending moments and lateral displacement of the piles. And if you compare 3D against 2D using Midas, you see a reduction of about 20 to 30%. Okay, and that's because not all the displacement goes to the bridge. Some of it just goes away from it. Okay, so you don't get the full demand of a 2D model. You get less than that. And in this case, for this analysis, the reduction was about 20 to 30%. Okay, so this is lateral displacement of the piles, and you can also get information about the bending moments and also about the shear. This is the bending moments in the different directions of the piles. Now, what I was trying to explain in the previous slide about the deformation of the soil, you can see it here. I mean, these are arrows showing the direction of the displacements, and yet most of the arrows, or many of them, point in the longitudinal direction. However, there are some other arrows that show that part of the soil mass displaces laterally, Okay, so that displacement doesn't create too much forces or demand on the bridge itself. Okay, so going from 2D to 3D was in this case, it helped you to understand the actual physics of the problem, and in this case also help you get a better estimate of what would be the actual demand on the bridge. Now, in terms of conclusions of this analysis, okay, I just wanna emphasize the importance in this type of problem of the inertial effects. Some efforts have been made in the past to try to incorporate inertial effects on simplified models, which I think, it is important and it's useful. However, the amount of uncertainty is not small. And sometimes you don't have really conditions that are applicable directly. If you go to the simplified approach and try to apply it to your case, sometimes there are some differences that can create some uncertainty. So simplified models, in my opinion, are a good way to go as a first step. But if you deal with this type of issues, you should go into numerical modeling, because, well, that lets you capture liquefaction, at least in a general sense, but also it gives you a better more information about the areas that are really going to be affected by liquefaction, how liquefaction is going to take place during the earthquake, and if it's going to be simultaneous or not with the inertial effects. Okay, because sometimes you may have conditions where liquefaction really takes place very late during the earthquake, maybe towards the end of it or early on. And that, if that liquefaction occurrence takes place at the same time or very close to the time where you have a large inertial effect, that's gonna create some problems in terms of design. The other, in this case, one conclusion is that using numerical modeling, in this case using 2D and also 3D, the results that were observed correlate reasonably well with what was observed in the field. And as more people start using this, we can start getting more confidence on the use of these type of approaches. And also something that I didn't point out too much, because, well, when we developed the model in Midas, really all the layers were horizontal, but the sloping of the layers for the problem of lateral displacement, it plays a large role. This is something that, of course, if you have enough geotechnical information, you can try to get a sense of that. If you don't have too many, usually we all use horizontal layers, but this is just a cautionary message to try to be careful with the use of only horizontal layers, because the sloping of the layers can increase the demands coming from lateral spreading. Okay, and with that, I finish my presentation. I again want to thank my former student Alvaro Gutierrez and also Angel from Midas for all their help to put up this presentation. And if you have any questions, well, please feel free to ask me. Thank you.